Testing. Okay, let's start, shall we? First, say hello to YouTube. Hey, my numbers are dwindling. Look at that. I'm going to assume it's because everyone's online watching, not because people stopped coming to class. Okay, let me just. I'm going to carry two microphones now, like this. Sorry. All right. So a couple announcements. First, the marks, midterm marks, have been posted. Very high marks, because I'll let you have a cheat sheet. You may not regret that. And also, those who wrote in SAS, I got the Scantrons today, so it'll be a couple days before your marks are posted. And we won't talk about the midterm yet, because some people have yet to write a version of it, those who are ill. And afterwards, Kahina will set up a special session where she will go over all the questions and answer them for you, and you can look at your marks there. So that'll be in a couple of weeks. Another announcement is that next Wednesday, I will not be here. But this will be class still, and the class will be taught entirely on YouTube. So you don't have to come, but you do have to log in. And if you can't make it there, that day will be a recording of it. So the way I usually do this when I can't make it is I will post a link to the live streaming video on the website, and you can click on it, and you can come here and use the Wi-Fi here, or stay home, doesn't matter. If you want to ask questions during the lecture, tweet them to me. And if you haven't got a Twitter account, here's your big chance to join the early 21st century. So yeah, that works out pretty well usually every year. Everyone got that? So Wednesday, if you show up here, don't be surprised that I'm not here. The door will be open. You can use the space. There it is. Okay. Any questions about that? Yeah. Dionandon. Last name. In fact, tonight I'll be at the Monk. I don't know what the Monk debates are. What are the Monk debates? Oh, well, there it is. I'll tell you about the Monk debate. So the Monk debates are a high-level academic debate that is sponsored by Peter Monk in Toronto. Get the top name scholars in the world. It happens every few months, and they're streamed for free on monkdebates.org or .com. And tonight it's Malcolm Gladwell versus Steven Pinker, and I hate Malcolm Gladwell. So I've dropped $200 just to go there in person, to be angry in person. So you can watch it tonight. See if you're angry like I am, and you can read my tweets. I tweet my anger. But yeah, so it's an opportunity to be intellectually engaged in real time. Right? Any more questions about next Wednesday? All right, good. So, you reading my tweets right now?
Yeah.
I'll allow it. Yeah. So I always photograph students that take exams. I usually take out the eyes. This time I forgot. So there's a picture of you on Twitter. So, am I violating your privacy? Probably. Okay. Let us begin. So it's going to be a fast lecture today because I got to catch a plane. But as always, things are done in 20 minutes or so. We're talking about chi-squares. Before we talk about the chi-square, which is probably the most common of the categorical variable analyses that you will do. Let's go over some of the things we looked at already. So we've looked at the ANOVA already. ANOVA was not on your midterm. That's okay. All right, you can look at it after class. Look at it. Focus. You can do this. Okay. So the ANOVA, as you remember, we talked about before your midterm. It stands for analysis of variance, and it's like a t-test when there's more than two categories. And there are three types of ANOVA, you will recall: the one-way, the two-way, and the n-way. What is the difference between the three? Remember? members. I know you're all kind of focused on the midterm, so I forgive you for not having this answered 3 times. Okay, the one-way ANOVA when there's one independent variable, and the 2 ways when there are 2 independent variables, and 3 ways, the n ways when there are more than 2. So in this class, we only do the 1 way, but I want you to know when to use the 2 way and the n way. Okay, so I already showed you the math for the 1 way ANOVA. So remember the 1 way ANOVA, as with all our tests, we have to compute something called degrees of freedom, which is some measurement of how many people we have in our sample. And for the 1 way ANOVA, we have k and n. N is a total number of people in our study. K is the number of groups, or the number of independent variables. Sorry, the number of levels of independent variables. And we have 2 degrees of freedom, the between groups and within group. These are the formulas for that. And we compute something called F. The F statistic is given by that formula. We went over that last time. And remember, just like our t-test and our z-test, if the one in the table is less than the one you compute, then we have statistical significance and we reject the null. That's the formula we're going to repeat over and over again, especially today, because the chi-square follows a similar kind of approach. Now, before we talk about the chi-square, the difference between parametric and non-parametric tests. Have you heard these words before in other classes? Probably not. So this is not a critical thing to know, except the terms will pop up again and again as you continue your career. A parametric statistical test is one typically where we've got a sample, and I compute a statistic, and I infer something about a parameter, hence parametric. More technically, a parametric test is one that relies upon a distribution in the population of something, like a t-test. A t-test has this t distribution. Remember, it gets higher as we have more people in it. The z distribution gets wider as more people in it. Okay, so those are 2 different distributions. We have the F distribution. The ANOVA is based on the F distribution. Anytime there's a distribution, usually there's a parametric test, but not always. A non-parametric test, though, is just none of the above. Okay. So the parametric tests that we know so far, the z-scores, the t-test, and the ANOVA are all parametric tests. The non-parametric tests are correlations. We're going to do correlations again, and the chi-square that we're doing today, and things related to these things. So again, it's not critical that you know that, but it's useful if you're looking to categorize the tests that you know. When do we use these non-parametric tests? We use them when our scales are typically not continuous. They're not integral or ratio. So they're nominal scales or ordinal scales. We're creating medians. You know what the Likert scale is? Ever do a survey and ask you, how satisfied are you with the tuition you're paying? Unsatisfied, satisfied, very satisfied. That's a Likert scale. Anything that's kind of ranked, that's an ordinal number. Likert scales are horrible to analyze, and yet everyone uses them. They all come to me after, I'm going to analyze this. Well, you didn't use it in the first place. But if you want to use it, analyze it, you use a non-parametric test. So, off on a tangent again. So anytime you haven't got this continuous measurement is often when we want to use a non-parametric test, or when the parametric test assumptions are violated. Remember some of the assumptions we talked about with the t-test and the ANOVA, things like, is our data normally distributed? Do we have independence? That kind of stuff. So especially when the sample sizes are small, we tend to violate those assumptions. So we have very small numbers, or if we got ordinal measurements, we gravitate towards non-parametric tests. So when you're selecting which non-parametric test to use, some of the things to consider are how many groups you're comparing. Like if I'm comparing whether or not the temperature affects the kinds of car that are bought in a given week. I'm looking at Ford versus Mitsubishi versus, I don't know, car companies right now. So 8 different car companies. So that 8 is different from comparing 2 companies. So the test I will choose differs. And it matters whether I'm comparing things between subjects or between groups. So all these factors come into play about how I'm going to select my parametric test or non-parametric test. So this is kind of what I want you to remember, is when we're looking at nominal measurements, remember what nominal measurements are? Categories that we can't compute averages for, like the province you're born in or your gender and things like that. And you've got 2 groups, we use a chi-square test. That's a non-parametric test that we prefer. That's the one we're going to look at today. If there's 3 more groups, we also use the chi-square test. But if we have ordinal measures, what's an ordinal measure? A Likert scale. How happy are you today? not so happy, moderately happy, very happy, extremely happy. That's a Likert scale. Then if there's 2 or more groups you're comparing, use something called a Mann-Whitney U test. And if there's more than 2 groups, a Kruskal-Wallis test. I will not tell you how to do these tests, just the chi-square, but I want you to know when you would use the Mann-Whitney U or the Kruskal-Wallis test. Good thing about cheat sheet. Have these things on it. Okay. Again, we'll only do the chi-square in this class, but I want you to know when to use Kruskal-Wallis. And in real life, also, it's you wouldn't do this by hand anyway. You have the computer do it, but you tell the computer which test to apply. Right? So far, we've looked at various scenarios of. Let's move the computer over here so YouTube can see what we're watching. We have one viewer. I bet that's Mateo. He's not here. Okay. He says that he watches this live every Friday. So I'm Mateo. Assume you're doing this. So we've looked at what to do if you're carrying the means of 2 samples. What test is that? It's on the slide already. You know what it is? It's a t-test, obviously, right? Comparing means of 2 things is always a t-test. And we have 3 different kinds of t-tests: the 1 sample, the 2 sample, and amongst 2 samples, independent and dependent. We've looked at what to do if you compare the means of 3 or more samples. That's the ANOVA. Just like a t-test, but with 3 different groups. And we've looked at what to do if we want to know if 2 continuous variables are related. That's a correlation. And in a couple of weeks, we're going to do a different kind of correlation, a ranked correlation. So look, you know this stuff already. Isn't that amazing? You can do somewhat advanced statistics already. That's incredible. Yeah. Well, I assume you can. You should be happy. You should be proud of yourself. So right now, you can probably do a small research study and analyze your own data using this information. So what do we do, though, if you want to see if categorical variables are related? You've already done a little bit of this. Remember the odds ratios and relative risks, right? Whether or not you smoke, yes or no, that's a categorical variable. Whether or not you got lung cancer, yes or no, that's a categorical variable. So you've already done that. That's a measurement of risk, though. And that's not typically a statistical test, but it kind of is. So the chi-square is what we usually do if we're trying to decide if categorical variables are associated. And it's written like that. That's the Greek letter chi. It's not an X. Okay. Chi-square test. The chi-square test and the relative risks and odds ratios are very similar in how they look. They're measuring something different. So it's easy to get them confused. But much like the relative risks and odds ratios, you're going to have to make a contingency table. And how you make that table ultimately allows you to do the math. And I found with some students on exam day, they get stressed out and they forget how to make the table, and that's when everything falls apart. So making the table ends up being the critical step. If you do that, everything else is just robotic. Extract the information from the question, put them in the table, and figure out the rest. So, example. We have 100 patients receiving intravenous medication via a new technology called a heparin lock. Okay? And they were assessed for complications at 2 points in the process, at 72 hours and at 96 hours. And we want to know whether the duration of the heparin lock is related in some way to the incidence of complications. So we have a number of complications that happen here, a number of complications that happen there in the heparin lock scenario. So in this question, extracting the information to place in the table can be challenging. Look at the numbers that we have. We know the total. We know 2 categories of events, and now we're going to see the number of incidents that happen. So this is a little confusing because I've given you 72 and 96. That doesn't matter. That's just 2 categories. The number 72, you're going to do nothing with. The number of 96, you're going to do nothing with. So it's a little misleading and confusing. So when you read a question like this, understand that sometimes asshole professors will throw in numbers just to confuse you, as we have here. Right. So what we're going to do now is test the relationship between these 2 categories in a cross-tab contingency table. So when we're dealing with chi-squares, we call it a cross-tab table because it's cross-tabulation. In the relative risk odds ratio example, it was a contingency table. We're saying that contingent upon whether or not you smoked, this is your incidence of lung cancer. Contingent upon whether or not you didn't smoke, this is your incidence of lung cancer. It's just a verbiage thing. But for your purposes, they mean the same thing because you got to make a table regardless. So the test we're going to do is Pearson's chi-square test. There are other kinds of chi-square tests. They all purport to do very similar things like modifications to the formula. Pearson's is the most common. Just be aware that there are different kinds. There's the walled chi-squared and Kruskal chi-squared, things like that. Okay, so what we're testing here is the differences in the proportions between the two groups the same or different? Right? So in this case, is the proportion of patients getting complications in this group versus that group, the 72-hour group versus 96-hour group. Of course it's going to be different. It's always going to be different. The question is it statistically different? Right? And this sometimes confuses people. You compute that the proportion of complications is maybe 72% in this group and 73% in that group. And so it's, oh, they're different. That's great. They're different. No, they're not necessarily, because there's sampling errors, and we're always looking at whether or not the margin of error is such that it's statistically different. That's what we're measuring here. So, as with all things, we begin with a null hypothesis. Null hypothesis for a chi-square is that the two categorical variables are independent, meaning they're unrelated. What does that mean? It means the proportions in the two groups are equal, statistically equal, not exactly equal. I mentioned maybe 172%, maybe 173%. That's pretty close. Right? It looks like they're different, but no, we're measuring are they, or more technically, do they come from the same universe? Remember that stuff where the proportions are all 72%. Remember, the null is that the variables are unrelated, meaning they are going to be the same number. The alternative hypothesis is that they are not independent, or they are related, right? Or that the proportions are not the same. Notice I'm not saying that one is bigger than the other. There's no directionality here. I'm just saying that they're different. And this probably reminds you of one-tailed tests and two-tailed tests. Remember, one-tailed tests have directionality, two-tailed tests don't have directionality. So you can say that this is very similar to a two-tailed test. We don't have direction. I'm not going to say overtly that it's a two-tailed test because there's some disagreement on whether or not a chi-square can be a two-tailed test. Don't worry about why that is. It has to do with the shape of the distribution. It's asymmetrical around 0. It's all kinds of annoyingly confusing mathematical stuff. So don't get yourself confused by that. Just remember that the null states that the two groups are the same, the two proportions are the same. The alternative says the two proportions are different. That's what we're measuring. Okay? So in this case, it's that the incidence of complications between the two groups are the same. That's the null. Nothing's going on, in other words. The alternative is the complication incidence and the duration of the lock, that is the two groups, are not independent, meaning they are related. What does that mean? It means proportions are not going to be equal. Okay, how do we do this? We're going to create our contingency table, or the cross-tabulation table, what we want to call it. We're going to have observed values and expected values. Now, what does that mean? The observed values are the data. That's what's in the question. That's what you've collected. That's what you're going to put in the table. The expected values are going to be the numbers that would have been there if the distribution were random. Right? And we're going to compute what that is. And according to the chi-square formula, we are going to compare these two in some mathematical way and determine if, in fact, the differences are significant. If the observed and expected are very similar, then nothing's really going on. Things are kind of random. If they're quite different, then something's probably going on. And of course, we have to compute our degrees of freedom, as we always do. And like everything, there's a different formula to compute degrees of freedom for this than there was in the ANOVA, than there was in the t-test. So here's our data. This is the cross-tabulation table. Notice vertically, I have my two groups. This is the 72-hour group and the 96-hour group. Again, these two, 72 and 96, are just there to confuse you. It doesn't matter what the name of the group is. The computer doesn't care. There's just two groups here. And here, my rows are the two other groups. They had complications, they had no complications. In other words, the incidence amongst this group of complications is going to be 9 over 50. And the incidence of this group is going to be 11 over 50. Now, these numbers here we call marginals. The marginals are the things on the edge of the table. Now, is this a 2x2 table or a 3x3 table? It's a 2x2, absolutely, because this variable has two levels. This variable has two levels. So the red parts are what we care about. This stuff here is all just the totals, the marginals. It doesn't count. So the assumptions for this chi-square test before we actually do it. Like with everything, the samples, the observations are randomly selected. We haven't gone looking for the ones that are extremely different from each other to introduce some kind of bias. Each observation independent. That means that the first guy who gets the complication doesn't affect the next guy who has a complication. Okay? So the odds of something else happening that's wrong is not related to a previous experience. So these last two are the critical ones. So each cell in your table, in your crosstab table, must have an expected frequency greater than 0. Not an observed frequency, an expected frequency. And we're going to compute that in a second, what that looks like. But it cannot be 0. And the second is the observed frequency must be greater than 5. Remember, the observed is your actual data, and the expected is what we compute. This has to be greater than 0. This has to be greater than 5. 5 or greater. The textbook says 10. But in regular practice, we say 5. It's wrong. Hear me? Okay. I'll write them someday. Okay. Now, we're going to talk about this observed and expected nonsense now. Because once you compute the observed expected stuff, you're going to plug it into this annoying-looking formula to get your chi-square. So the chi-square here, that's the thing that we want to compute. The O's are observations. The E's are the expected values. We can divide by the expected. We can add them all up. And that gives us the total of the chi-square value that we will then compare to the back of the book, as always. Right? So let's do it now. This is our data again. Right? So set up that way. The observed frequencies are what is already in the table, the red parts here. Right? So observed is always the data that we have from our study. Marginals are here. The expected are going to be computed by using the marginals and multiplying them out. So the expected for this square here is going to be that, multiplied by that, divided by that. Like so. These are the marginals. Looks like this. So 50 times 20 divided by 100 is the first expected one. For this one, it's going to be 50 times 20 divided by 100. For this one, it's going to be 50 times 80 divided by 100. For this one, it's going to be 50 times 80 divided by 100. Get the point? So you just go with the marginals that correspond to each cell and divide it by the total, and that gives us the expected values. Let's do the math. These are our expected values. And the original numbers are observed values. Now, right away you look at it, right? You got 9 in this cell, you expected 10. That's not very different. You observed 11, you got 10. That's not very different. 440, that's not very different either, and that's not very different. Right away on its face, you see that the expected numbers are not that different from the observed numbers. So you know probably, is there something going on or is there nothing going on? There's nothing going on, probably. When the expected and the observed are very similar, you probably have a null hypothesis situation. You're probably not going to reject the null. You're probably going to find that the proportions are the same. So let's do the math. We plug in our numbers into, I recommend a spreadsheet situation like this. So here are our cells, 1, 2, 4 cells. Our observed numbers, our expected numbers. We subtract them first, and we square the subtractions. Subtract them all. Again, we square that number. Why do we square it? Remember, to get rid of the minus sign. Then we divide by E again, as the formula dictates. We get that number, add them all up, we get 0.25. That is our chi-squared number. Straightforward. Very simple. That's a chi-squared. What do I do with this now? I compare it to the back of the book. But in order to compare it to the back of the book, I need to compute degrees of freedom. So this is the formula for degrees of freedom in chi-squared. It's number of rows minus 1 multiplied by the number of columns minus 1. In this situation, how many rows do we have? 2 rows. How many columns do we have? 2 columns, because we only care about the data bits. 2 columns, 2 rows. So degrees of freedom is going to be just 1. 1 times 1 is 1. Straightforward. So we have a chi-square of 0.25. We have a degrees of freedom of 1. We go to the back of the book. I think it's page 416. As always, back of the book says 3.84 is the chi-square that they compute. Ours is less than that, so we reject the null and fail to reject the null. Our number is lower than the book's, so fail to reject. So when our number is higher, that's when we reject. Okay? So we conclude what? Always answer questions. Yes?
Complication rates of unrelated situations.
It's on the slide. That's right. Straightforward stuff. Now, this was a 2 by 2 table. It's possible to do a chi-square with any number, rows and columns. 12 by 100 table, 1,000 by 20,000. It's unlikely that's possible. The same formula applies. Right? So probably the most I would have asked you to compute is like a 4 by 3 or something. Otherwise the math gets clumsy. But recognize that the same formula applies. So the steps again, we state our null hypothesis, which is always nothing's going on. In this case, it's always the proportions are going to be the same in both groups, or the two variables are not related, or they're independent, all mean the same thing. The next thing is we could create a contingency table or the cross-tab table. You check your assumptions. The critical assumptions, meaning you must have at least 5 in each of those tables. Let's go back and look at that for a second. Here we go, right? So remember the assumptions here. My observed here are 9, 11, 41, and 39. They're all 5 or over. That's great. My expected are all over 0. That's great. The two major ones are satisfied. And it's amazing how many times they're not satisfied. I've seen published papers in which the assumptions are violated and the papers are just wrong. Reject them. Okay. I was examining a PhD defense earlier this year, and the student had cell sizes that are too small for the chi-squares. The thesis was wrong. It's all wrong. Passed her anyway. Yeah, it's a quality of education. Okay, so you check your assumptions. You compute the expected frequencies. You compute your chi-square, and you assess the null hypothesis by looking in the back of the book or using an online calculator. So some notes here. Like I said, we've used a 2 by 2 table, but you don't have to. You can use any size, so long as each of the cell sizes has at least 5. Okay? For example, is there a relationship between the make of car, whether or not they stop fully at a stop sign? Right? So and here we have make of car is Ford, Chevy, Toyota. The stop sign it says fully, partly, not at all. What's the size of that table going to be? 3 by 3. Right? 3 levels. 1, 2, 3, 3, 3. Okay. Straightforward. So this part might be a little confusing, but the general logic is that you're looking at what the expected frequencies are what the result would have been if the null hypothesis were true. So what you're just testing that. You're testing to see if the null hypothesis, if its reality is played out for you. That's essentially what we're saying here. This stuff is a little confusing, but I'm here for completion's sake. Remember, we're looking to see if the observed minus the expected values are different or not. If they're the same, they're going to be 0. So if I were to actually draw a histogram of all the possible chi-square values, it's going to be around the number 0. So 0 is the most common thing because 0 is the observed minus the expected. It's actually an asymmetrical distribution. It's actually skewed. That's why I don't draw a picture of it here. We've done so many symmetrical distributions, like the normal distribution. If I show you the chi-squared, it might be a little confusing. But that's the important part here. It's around 0. So what do you do if you have fewer than 5 in your cell? Well, we do something called a Fisher's exact test then. Fisher's exact test is like a chi-square, but it accounts for the fact that we have small cell sizes. And you may ask yourself, why don't we always do the Fisher's exact test then? It always works. And sometimes we do. So SPSS, the current version, knows automatically. If the cell sizes are too small, it will give you the result of Fisher's exact test. If the cell sizes are large, Fisher's and chi-squared, it gives you the same number anyway, so it doesn't matter. So again, I'm not going to ask you to compute Fisher's exact test, but I want you to know that's what you would use if the cell sizes are small. Okay? So the same as a chi-square, but cell sizes. So how do you do in SPSS? You go to Analyze Descriptive Crosstabs, you select here on Statistics the kind of test you want, and you can select a chi-square. Straightforward stuff. That's your homework. Look at that. Is that a 20-minute lecture? Right on. That's the way it's supposed to be, right? No questions? All right, good. I won't see you Wednesday. I'll see you online on Wednesday.